about refraction of light at plane interface. This is the chapter name. Over here, after we learn about refraction, we'll be also learning about total internal reflection, which is a phenomenon, and how it helps out in case of optical fibers. Now that's the name of the chapter. Now refraction of light, this is particularly for class 12 students. So we very well know from our previous knowledge that refraction of light actually means when a ray of light travels from one optically denser medium to another optically denser medium. That means these two mediums have got different speeds of light in them. That means that speed of light is somewhat different over here compared to what is there in medium second. Now, this particular ray which came and strikes this plane interference over here is called incident ray. This line which I have drawn is called normal. It's always 90 degrees to the plane surface. The angle between them is called angle of incidence. This is what we know. This ray, now if you see, has actually bended towards the normal. Remember guys, when a ray of light travels from one medium, enters into second medium and it bends towards the normal, it happens because the speed of light has decreased. Whenever speed of light decreases, the ray of light bends towards the normal. This phenomena where the ray of light actually has not travelled in a straight line but bended towards the normal is known as refraction. Now this is a particular case of refraction in which the ray of light has travelled from an optically rarer medium to optically denser medium. We say whenever a ray of light moves from optically rarer to an optically denser medium, it bends towards the normal. Just opposite happens when ray of light moves from optically denser to optically rarer. For this, now I'll be changing the direction of light. Now, if I remove these signs and I put an arrow over here, which means the ray of light has started from optically denser medium and is moving towards optically rarer medium. If you see now that the ray of light bends away from normal. These two cases actually refers to refraction of light, where the ray of light actually tends to deviate away from its original path. Remember also, if a ray of light moves along normal, that means it overlaps the normal, then it does not deviate but actually traverses along its same path, that means the normal. So summarizing the whole, we can say when a ray of light moves from optically rarer to optically denser, it bends towards the normal. When it moves from optically denser to optically rarer, it bends away from normal. And if it moves along the normal, it remains undeviated. Now that was refraction. Let's come to Snell's law. According to second law of refraction, when we say a ray of light moves from optically again rarer to optically denser medium, let's say, it bends towards the normal, then the ratio of sine of angle of incidence to sine of angle of refraction is always a constant, provided external parameters remain constant. When we say external parameters, I actually mean the temperature, the pressure of the environment remains same. If external parameters are same, then ratio of sine of angle of incidence to sine of angle of refraction is a constant, and this constant is called refractive index. I'll be representing it by n. If you see over here, I have written 1 and 2 as suffix. This one stands from where your ray actually has originated. This originated from the first medium, that means it started from the first medium. So I say it started from first medium and entered into second medium. This refractive index is actually a ratio of sine of angle of incidence to sine of angle of refraction. This is what is Snell's law. Refractive index can also be written as the ratio of velocities in the first medium to the second medium. That means the speed of light in the first medium to speed of light in the second medium. It can also be said as the ratio of wavelength of light in the first medium to that in the second medium. We'll be talking about wavelengths when we will be studying about wave optics. Right now, these are the formulae which we'll be using in this chapter. Now, the reason I wrote over here why refraction occurs is that speed of light is different in different mediums. Next heading, students, is refraction through a rectangular glass slab. Over here we'll be deriving an expression for lateral displacement. Now what actually is lateral displacement? Let me explain this to you by the help of this diagram. This is a glass slab which I have made over here. Ray of light enters, strikes the medium and enters this glass slab. That's the first refraction. So this particular angle of incidence is first angle of incidence. This angle of refraction is first angle of refraction. Hence I have used I suffix 1 and R suffix 1. After that, when the ray of light comes and strikes this glass slab at the second interface, it leaves the glass slab and enters the rarer medium, that's air. Therefore, the second refraction, this particular angle I have taken as R2, which is angle of incidence. Triangle ABT. Over here in triangle ABT, I have taken cos R1. It's a right angle triangle, so cos R1 can be written as T, which is thickness of glass slab, on AT, where AT is the hypotenuse of this triangle. So cos R1 is small t upon A capital T. I have taken that as first equation. Now look at triangle ATM. In this triangle, this is the path of ray it would have taken if the glass slab were absent. अगर glass slab नहीं होता तो ये ray of light अपनी इस original path पे travel करती. But the actual path of ray of light which it passes through after passing through glass slab is this way. The perpendicular distance between them is called lateral displacement. We need to find an expression for lateral displacement. So now look in triangle ATM. This is I1. So this whole angle should be I1. It's vertically opposite angle. So this particular angle is I1 minus R1. I have taken in triangle ATM sin I1 minus R1 as perpendicular, which is D, lateral displacement, upon AT, where AT is hypotenuse. Let this be equation first, let this be equation second. I have divided now the first equation by the second equation. On dividing them, if you clearly see AT gets cancelled out, making D the subjective formula. We get D or lateral displacement as T, where T is thickness of glass slab, sine of difference of angle between incidence and refraction multiplied by sec of first angle of refraction. This proves us the expression for lateral displacement. Next heading is critical angle. Remember, when a ray of light moves from denser to a rarer medium, we very well know it goes away from normal. Let's say this is angle of incidence I and this is refracted ray, so this becomes angle of refraction. Now if we go on increasing angle of incidence, angle of refraction also goes increasing. There comes a particular time when angle of refraction, the ray or the refracted ray just overlaps the boundary separating rarer and denser medium. In this case, the angle between normal and refracted ray becomes 90 degree. Such a particular angle of incidence is known as critical angle. So the condition for critical angle should be that ray of light should start from denser medium, it should enter the rarer medium, and angle of refraction should be 90 degree. Remember these two conditions. So now ray starts from denser, moves to rarer. In such a case, this angle becomes angle of incidence or critical angle, which I wrote as sin C. When the angle of incidence becomes critical angle, angle of refraction is 90. So I wrote sin 90 over here. On interchanging the mediums, that means if I pick up rarer as the incident ray and denser as refracted ray, these terms also gets interchanged. This becomes sin 90 and this becomes sine c. We very well know sine 90 is 1 and inverse of sine is cosec. So refractive index in case of critical angle is cosec of its critical angle. Next heading is total internal reflection. Students, total internal reflection, over here again the ray should start from denser medium. We very well know for critical angle, the ray should start from denser medium, as we say, enter to the rarer medium, and angle of refraction becomes 90. This we already learned. If ray of light starts from denser medium and angle of incidence becomes greater than critical angle, I repeat, ray should start from denser, enter the rarer medium, angle of incidence becomes greater than critical angle, then the ray goes back to the same medium from where it emerged. That means the ray is not going to rarer medium anymore, it moves back to the denser medium. And this phenomena is known as reflection, not refraction. So this phenomena particularly is known as total internal reflection because ray started from denser medium and the angle of incidence becomes greater than critical angle, so the ray traverses back the denser medium. This phenomena is called total internal reflection. With this we are over the chapter. Thank you. Please don't forget to like and subscribe my channel. Tomorrow we'll be dealing with the numericals of this chapter. Till then, goodbye. Thank you.